Okay, good afternoon or good morning or good evening, wherever you are. Welcome to our webinar on bioprinting, post-printing solutions, and focusing on 3D tissue bioreactors. So before I begin, let me first introduce myself, since not everyone here knows who I am. My name is Dr. Mayasari Lim, and I'm CEO of a small startup based in the Bay Area called SE3D. We focus on desktop bioprinters, and we work with many universities and schools and colleges to bring bioprinting into the classroom. So today, our focus is going to be more on post-printing solutions, which is on tissue bioreactors. And our partner actually is based in Singapore, and unfortunately, they're not here to join us today since it's very early in the morning in Singapore. So today I'll be representing them on their behalf to share with you some of the more interesting things that they're working on, and really focusing on the tissue bioreactor that they're introducing. So we have Dr. Lau, who is the managing director and from Quintech Life Sciences. So just to give everyone kind of an overview of how we're going to conduct this session, basically we'll share a couple of slides, and if you do have questions during the webinar, feel free to type in the questions that you have, and at the end of the presentation, I will be happy to answer any questions you might have. So in the meantime, I would request that everybody mute their microphone so that we don't have any background noise in between. So thank you for doing that. Okay, so let's start with looking at, bioreactors in general. So I think when we mention the word bioreactor, for most of us, what comes into your mind probably is this classic stirred tank bioreactor that you probably see in a lot of the manufacturing facilities, right? And there's different modes of operating a traditional stirred tank bioreactor. It could be a batch mode, a fed batch, or a continuous mode where you have continuous perfusion going in and out of the system. So most of the applications with traditional bioprinters are focused on fermentation, wastewater treatment, food processing, and also drug and protein manufacturing. And you can see here an example from GE Life Science, their small stirred tank bioreactor. The classic ones are stainless steel, and obviously you have all these tubings and computer to operate and automate the system. However, if we start looking at 3D tissues, whether it's bioprinted tissues or just 3D tissues, cells on scaffolds, such as in the classic tissue engineering application, we know that it's not easy, right, to grow and maintain these 3D tissue in culture. And there are many challenges, and there's many parameters for us to consider, from the cellular components to the scaffold design, and also to the signals that we actually introduce to the cells during the culture period, right? So here, just to kind of give you a really high-level overview, what are some of the considerations and also challenges that you need to think about, right? So for the scaffold, for example, we need to consider the structural properties, the biocompatibility, porosity, the degradation rate potentially, and maybe the topography of the scaffold as well. And then on the cellular side, there's also different types of cells we need to consider, and each of them have their own unique requirements. Sometimes we may have cold culture systems as well, and those also bring a new set of challenges. And then finally, when you think about signals that you feed into the cells, they're not only just the biochemical signals where we're talking about growth factors or nutrients, but we also need to think about mechanical and electrical signals that may be necessary to stimulate these cells to grow into the desired tissue and functional aspects of them. So in general, when we talk about the requirements for a bioreactor for tissue engineering or a bioprinted tissue, here are some of the general guidelines that we should think about. So first, we need to provide an environment that is able to maintain the physiological requirements to support cell growth, right? So here, the basic ones are nutrients, oxygen, and growth factors. And secondly, when we look at the bioreactor, we also need to think about how is the bioreactor design and process facilitating and promoting a uniform cell distribution and cell growth, right? So those are also very important considerations, especially when we start looking at 3D tissue structures and larger constructs as well. Uniformity of the cell in terms of the growth and the viability is really critical. The next one to think about is, which is along the lines of nutrient requirements, is how can we increase mass transport? Because with the classic 2D cultures, right, you're very much limited by diffusion, and there's only, and typically because of the way the 2D culture systems are designed or set up, many of the cellular constructs in 3D are limited by the amount of diffusion that nutrients can flow inside the scaffold, right? So as a result, a lot of the 2D cultures do not actually provide a homogeneous cell growth within the construct, and you often get like a necrotic center or uneven cell growth inside the construct, right? So here in the tissue bioreactor, there's an opportunity for us to increase mass transport either by diffusion and convection. So the next consideration is also to look at how can we expose cells to the necessary external kind of stimuli, right? So in this case, it could be an electrical stimuli, or it could be a mechanical stimuli, or it could be both electrical and mechanical stimuli that you need. Finally, one of the goals of the bioreactor should also be designed in such a way where you could ensure reproducibility. So thinking about what kind of monitoring processes or systems should be in place, and the availability of automation should also be a very important consideration here. So in terms of different types of tissue bioreactors that are currently being used, we'll start with some of the more common ones. So this one is almost, looks almost like the stir tank bioreactor, which actually in many ways it is. And in this case, we have, as you can see from the diagram, the cell scaffold constructs are actually attached to these vertical needles, and they are fully immersed in the culture media. And typically they're hanging from the top of the vessel, right? And at the bottom, we also have sort of a stirring mechanism, typically by a magnetic stirrer, that basically allows you to mix the media very homogeneously inside the vessel, right? So mixing is important because you want to minimize concentration gradients, and you also want to enhance the mass transport into the center. So the other bioreactor that is, the second bioreactor that is also very commonly used or seen in tissue engineering is the rotating wall bioreactor. And this is originally designed by NASA to stimulate microgravity. So as you can see in this picture, the rotation of the vessel will affect whether or not you achieve microgravity, right? So if the rotation is too low, obviously that you won't be able to achieve microgravity. But when you rotate it at the right speed, you will be able to then achieve microgravity and stimulate these environments for testing different kinds of tissue. So a lot of the work has been focused on bone tissue engineering and bone tissue regeneration, right? And a lot of these experiments have shown that there is an increased proliferation of the cells in the rotating wall bioreactor system. But as far as osteogenic differentiation, some of the results are mixed. And I think it really depends on how the cell type and also the conditions that are that are actually specific to the experiment itself. So one of the limitations in this design is that typically it's limited to smaller constructs, since the mass transport into the core of the scaffolds are not necessarily optimal. And also, because of this very low shear stress environment, it may not be so ideal for osteogenic differentiation. And therefore, we sometimes see these mixed results from these studies. Another really common bioreactor for tissue engineering is the perfusion bioreactor. And here you can see two basic configurations. Here, obviously, we're utilizing a pump to actually transport nutrients and oxygen through the culture chamber. And there's really two basic setups: the direct perfusion, where the media is actually forcing a fluid in through the samples into the center, versus the indirect perfusion system, where actually the convective forces are actually minimized around the surfaces of the constructs, because the fluid basically will flow across the minimal resistance. Another one that is very common for blood vessel or any kind of vessel tissue engineering application is this tubular pulsatile bioreactor, where basically we're stimulating the construct both with a hydrodynamic and mechanical stimulation. So the pulsatile flow and also continuous perfusion is providing sort of the right cues to enable blood vessel tissue engineering. And a couple of successful studies have really shown that this approach works in terms of creating vascular tissue using smooth muscle cells seated on these tubular polymer scaffolds. So perfusion in this case is really improving the tissue growth and metabolism, and really enhancing mass transfer and reducing the concentration gradients inside the system. So what kind of mechanical stimulation are commonly being used? So a lot of the tissue engineering applications, as you can see, cartilage, bone, muscle, cardiac, skin, tendons, ligaments, and blood vessels require some kind of a mechanical stimuli. And we know that mechanical transduction is necessary not only in stimulating functional differentiation of many tissues, but also in terms of giving them the right signals to induce the signal pathways for these cellular functionalization. So in the case of cartilage tissue engineering, for example, there are a lot of studies that have already shown mechanotransduction stimulates biosynthesis of extracellular matrix molecules, and physical stimuli like shear stress or compression. Also, very importantly, it not only alters sort of the distribution of the structural components inside the cells, but they're also inducing biochemical inputs that allows you to modulate these different signaling pathways within or between cells. So again, these are very important and critical for many of these tissue applications. So today I want to kind of highlight the T-cell bioreactor. And this is actually a technology that was developed by one of my colleagues, who is a professor at Nanyang Technological University, where I was previously a faculty, and Professor Teo Sui Hin, and also Diet Ma, and a few other, I guess, researchers were basically the inventors of this novel bioreactor. And I'm really happy to have this opportunity today to share sort of some of the really exciting work that they're doing, and hopefully to also introduce this system to more researchers. So this is the T-cell bioreactor. They have basically a patented biaxial revolution, which basically allows you to sort of spin and tumble inside the bioreactor. And this design specifically allows a very highly efficient fluid transport within the scaffold, which you'll see the results shortly. And also the spherical vessel itself also provides sort of a unique biaxial flow regime to be generated inside, which allow very uniform mixing. Other ways that you could use the system is also uniaxial. So if you prefer to just do a single rotation, you could do that, or you could also have like a swing mode. So this is some data that that they have provided in terms of results that they got for bone tissue engineering. So as you can see from these images, as compared to conventional 2D cultures, you definitely get a lot better proliferation and also uniformity of the cell growth inside the scaffold tissue, as you can see from the left side of the picture. And then when we looked at the osteogenic properties of these tissues that is in culture, you could see that the T cell again provided better osteogenic differentiation profiles and much more uniform profiles as well. And then finally, on the far right, we have some data showing mesenchymal stem cell expansion of microcarriers could also be generated using the T cell bioreactor. Another set of data that I'm not sharing here is also it's used for T cell expansion. So the group has also, a couple of the researchers have also started working on T cell expansion using this bioreactor system. So here are some of the applications that have already been tested using the T cell bioreactor: bone regeneration, biomaterial testing, adipose tissue for breast reconstruction, bone marrow stromal cells, cartilage, heart patch, co-cultures, and also stem cell expansion. Other modules that are available, so you can see here, the chamber itself, there's 3 different sizes that comes. You can choose whichever size you need for your application. So the smallest one is a 50 ml, and the largest one is 1,000 milliliters, which is 1 liter bioreactor. You could also choose to have dual perfusion in the event that you need to have 2 very unique media requirements for the cells that you're trying to grow. So you could also set it up for dual perfusion as well. And finally, that's it. I think this is all that we have today as far as sharing the slides and information. If you have any questions at this point, I welcome you to type in the questions that you might have on the chat box, and I will be happy to answer any questions. Okay, so if no one has any questions at this point, I will be closing the session in a few seconds. And if you do have questions later on at any point, or if you would like to have more kind of in-depth technical information about the bioreactor, feel free to drop us an email at info@sc3d.com. If you also wanted to do like a one-on-one in-person Q&A with Dr. Low at Quincy in Singapore, you could also drop me an email and let me know, and we could set up a one-on-one meeting with the Singapore partner as well.
Can I ask for, hello, can you hear me?
Yes, I can hear you.
Hi, thank you. Thanks for the presentation. It's really nice. I'm just concerned whether can we use this bioreactor for hydrogel-based scaffolds?
Yes, you can. There are obviously hydrogel-based scaffolds are very soft, so you could still, put it in the spindle, or I guess if you rotate it, you could kind of simulate microgravity as well. So more similar to the, the rotating wall vessel type of an approach.
Okay, so I was just concerned if means while just fixing the scaffold in the scaffold,
yeah,
are we gonna penetrate this? I mean, are we gonna disrupt the scaffold in some fashion? How are we gonna fix that to the reactor?
absolutely. So that is definitely a downside. If you fix the scaffold onto the spindle, then you are going to have like a hole in the middle.
Yeah.
That's just, the
We
way.
don't have any other option.
Yeah. So I
Okay.
think the other option, if you don't want any holes or anything inside the scaffold, then I would recommend just, throwing the scaffold inside the bioreactor and just kind of spinning it so that you could kind of simulate microgravity.
Oh, okay, cool. Thank you. Thank you very much for
You're
your
welcome.
answer
Thank
and
you
your
for the
presentation.
question.
Thank you. Yeah. Bye.
Bye. Any other questions from other participants? Nope. Okay, so I will close the session. Thank you again, everyone, for joining us. And if you have any questions, feel free to reach out at any time. Thank you.